Good morning and good afternoon to jury members offline and online, and good morning to you all. Today, Fernando Davalos Hernandes will defend his doctoral thesis entitled Supercapacitor Energy Storage System based on Modular Multilevel Converter with Embedded Self-Balance Control. The defense procedure is as follows. First, I will introduce the jury members and the candidate. This will be followed by the candidate's presentation up to 40 minutes. After the presentation is finished, we turn to the questions. And this will be as follows. First, questions from the jury members. And then in the jury members, so the external members of the jury get to ask their questions first. Then the Skoltech members of the jury follow. And if we have people attending the defense and willing to ask a question, I may allow them to ask their question to the candidate. Then, before we do the closed deliberation, we will have the word of the supervisor. Then, after we have among the jury members discussed the defense, we will announce the outcome to the candidate. So, Fernando, you may start when you're ready your presentation. Excuse me, no, I missed it. I'm too eager to listen to you. Yeah, so yes, the jury presentation. So we have among us, so we welcome our colleague Pallavi Bhatnagar, who is a senior member of IEEE. So Pallavi received her bachelor in electrical engineering from Lakshmi Narayan College of Technology in Bhopal, India, and a PhD degree from the Department of Electrical Engineering at Maulana Azad National Institute of Technology, also in Bhopal, India. Then she started as an assistant engineer her career with All India Radio in Bhopal. And her career developed as head of product development in Nucleus Electro Enterprises Limited in Bhopal. In 2005, she joined the National Thermal Power Corporation of India as an engineer. Pallavi has more than 23 years of experience in teaching, and she was among us at Skoltech in 2019 as a research scientist in the Skoltech Center for Energy Science and Technology. Now she is currently working as associate professor at the Mechatronics Engineering Department at the Manipal Institute of Technology. And she also performed research with the Sustainable Energy Research Center in the Sultan Qaboos University in Muscat, Oman. She's also working on a government-funded research project on a 3-level bidirectional high-power density charger for electric vehicles. She has co-authored a book entitled Multilevel Inverters, which is published by Elsevier. And her research interests include power converters, photovoltaic systems, LED-based lighting, and electrical vehicle charging infrastructure. Among us today in Moscow, we're happy to have Dr. Vedran Peric, who is an electrical engineer with more than 10 years of experience in industry and academia. So he is currently the head of the Research Center for Combined Smart Energy System at the Technical University of Munich. So his research field is in dynamic stability, operation, and control of smart grids. And he has a particular focus on the integration of electric systems with district heating and cooling grids. His group is operating a lab where they perform high-power hardware in the loop experiments up to 1 megawatt on a small but very flexible microgrid. And the experiments aim to validate theoretical results on the real hardware. Online with us today, our colleague, Dr. Piotr Vorobyov, who is Senior Research Fellow at the Nanyang Technological University since August 2023. So Dr. Vorobyov received his PhD degree in theoretical physics from the Landau Institute for Theoretical Physics in Moscow in 2010. Then from 2015 to 2018, he was a postdoctoral researcher at the Department of Mechanical Engineering at the MIT in Boston. And from 2019 until 2023, he was assistant professor and associate director at the Skoltech Center for Energy Science and Technology. So the research interests of Dr. Vorobyov include a broad range of topics related to power system dynamics and control, low frequency oscillations in power systems, dynamics of power system components, multi-time scale approaches to power system modeling, and the development of plug-and-play control architectures for microgrids. With us here in Moscow, we have our colleague, Professor Yelena Grezina, who is assistant professor at the Skoltech Center for Energy Science and Technology. Yelena graduated with honors from the Moscow Institute of Physics and Technology, and she obtained her Candidate of Science degree from the Institute for Control Sciences at the Russian Academy of Sciences in 2007. She recently defended and was awarded the title of Doctor of Science in Computer Science, which is the Russian equivalent of the habilitation. So she received it from the Higher School of Economics in 2022. Since 2018, Professor Grezina has been the director of the Energy Systems Master's Program. At Skoltech, Professor Grezina's research focuses on the development of computationally efficient methods for analysis and optimization of power flow. She also develops a mathematical framework for the optimal functioning of smart energy systems of the future, including load identification methods and coordinated electrical vehicle charging protocols. Yelena leads research projects on the assessments of the effects of renewable energy sources integration into the Russian power grid and artificial intelligence for optimal integration of renewable energy resources in microgrids. I am the jury chair, so my name is Professor Warden. I graduated with a master's degree in statistical physics in France and a PhD in physics from Heriot-Watt University in the UK. I also hold a Master of Art in project management. Before joining Skoltech, I developed my career at different places, such as Glasgow University, the Tyndall National Institute in Ireland, CNRS laboratories in France, and the Russian Quantum Center. So my current research activities are quite diverse in physics, but also in engineering. And in physics, I'm interested in solid-state physics and non-equilibrium thermodynamics. But I also lead some activities related to energy systems at Skoltech. So I joined Skoltech 6 years ago as a leading research scientist to work on the project integration and control of heat and power systems with variable loads. It was a project funded by the Next Generation Skoltech MIT program. I am currently an associate professor, and my group is the Energy Conversion Physics and Technology Group at the Center for Digital Engineering. I am currently the director of the Engineering Systems PhD program and chair of the Skoltech Educational Committee. So Fernando's supervisor is Professor Federico Martin Ibanez. So he received his engineering degree from the Technical National University at Buenos Aires in Argentina in 2008. His PhD degree in 2012 from Universidad de Navarra in Spain. He has 15 years of experience in electronic design and mostly in experimental laboratory activities. He worked as an electronic designer in the National Commission of the Atomic Energy in Argentina. And he was also a researcher in the field of power electronics from 2008 until 2016 at the University of Navarra in Spain. So Federico has participated in several European and national and regional projects related to power electronics. In those projects, he designed, developed, and tested several DC-DC and DC-AC converters for energy storage and electrical vehicle applications in the range between 1 to 100 kilowatts. Currently, he leads the Smart Grid Laboratory as an associate professor at Skoltech. His research field is mainly power converters for grid and electrical vehicle applications, particularly grid-forming inverters, resonant and multi-port converters. His articles are published in leading international journals and at conferences. At Skoltech, Professor Ibanez teaches 2 courses on power electronics and smart grids. Last but not least, our PhD candidate today, Fernando Davalos Hernandes. So he received his bachelor's degree and specialization degree in electronics and robotics at Universidad Panamericana at the campus of Aguascalientes in Mexico in 2017. And his master's degree in science in 2019, conducting a collaboration at Skoltech as a research intern, focusing his experiments on energy storage systems based on modular multi-level converters. So as a result of that collaboration, he then joined the doctoral program in engineering systems at Skoltech and continued his research in power electronic systems and with a particular focus in energy storage systems. So his results are the object of 4 publications as first author. So now I'm very happy that we can come to the candidate's presentation. I was looking forward to it. So please, Fernando, you may start when you're ready. You have up to 40 minutes.
So Fernando.
Hi, everyone. My name is Fernando Davalos, and I will be talking about my thesis entitled Supercapacitor Energy Storage System based on Modular Multilevel Converter with Embedded Self-Balance Control. My supervisor, Professor Federico Martín Ibáñez, and I am applying for the doctoral program of Engineering Systems. First, I want to introduce the thesis structure. First, I will be covering the introduction, then the literature review, and in the literature review, I will be talking particularly in high-gain DC-DC converters, then multi-level converters, modular multi-level converters and their basic submodule topologies. And at last, I will be presenting a comparative of actual energy storage systems based on the modular multi-level converter. Then I will introduce the proposed modular multi-level converter, then the experimental results and validations, and finally, the conclusions and the future work. So in the introduction, first I want to talk why we need to have the energy storage systems deployed in the grid, because if we want to continue the integration of renewable energy sources, and if we want to decommission all fossil fuel generators, we must adopt the energy storage systems. They should be placed between the transmission lines and the distribution grid, and they will provide the controllability that it is needed for the grid, so that the utility or the grid operators can have another degree of control. So why we need this? Because renewable energy sources are with a stochastic behavior, and then we require some form of buffer energy or temporary electricity storage. As we know, gas turbines cannot be commanded to abruptly stop. They have just a small flexible range, and with an energy storage system, we can inject or absorb power from the grid. So we can increase the allowed power range. There are multiple forms to store energy. or electricity. Most of them will require a DC-DC converter, and then if we want to connect to the grid, a DC-AC inverter. I'm proposing to use supercapacitors because they have the high power ratings, the highest power density, and they have up to 1 million cycles of lifetime. So based on this, the research question that I came up is what are the best features of a power interface for a supercapacitor energy storage system? And based on that, I proposed the following methodology. First, I will be covering the literature review and analyzing how the traditional energy storage systems are designed. Also, I want to focus on which are the better topologies for the power conversion and the state of the art for supercapacitor energy storage systems. After that, I will do the gap identification and propose a system that can satisfy all the gaps. And I will validate this through simulations and modeling, particularly focusing on the static analysis, the dynamic analysis, the balancing algorithm, and the losses analysis. And finally, validate this through a prototype, doing the AC generation test, the step response test, the balancing tests, and the efficiency results. But the disadvantage with supercapacitors is that they are usually low voltage devices, and also they behave like a normal capacitor. So if you want to extract at least 70% of energy from them, you have to go from the maximum voltage to the voltage divided by 2. So you have a wide voltage range, and also if you want to increase the voltage of the supercapacitors, you have to put them in series. But if you overcharge the supercapacitor, you can decrease the lifetime of it. So that's why you need a balancing system to regulate the charge presented in the supercapacitors. We have two options. One is using the active method, and the other one is using passive methods. The passive method will burn the extra amount of energy just to balance the supercapacitors. And the active method will take this extra amount of energy and will transfer it to the most discharged supercapacitor. But a traditional system will have these 4 stages. We will have first the supercapacitor cells or the energy storage device. Then we will have the balancing system that I'm mentioning. And after that, we have the DC-DC converter. And if we want to connect to the grid, then we will need a DC-AC inverter. And if it is required by the grid codes of the country, an isolation transformer. The problem with this traditional energy storage system is that there is no flexibility for upgrades or future scalability. So this is like the main concern. And also these stages have to be designed for this power constraint. And maybe one of these stages fails, the whole system will fail too eventually. So in the literature review, I'm focusing on the high gain DC-DC converters, the multi-level converters, the modular multi-level converter, and then the comparative, as I already mentioned. Why I'm focusing on the high gain DC-DC converters? Because this is another solution for supercapacitors. They can provide, reach higher voltage levels from the supercapacitor stack. And then this with a single DC-DC stage, we can then interconnect the DC-AC inverter. But also, because we are using supercapacitors, we need to have a converter that is able to operate in the wide input voltage range efficiently and do this power conversion. Particularly, I was exploring these 2 solutions. The top solution has also a battery in the first port and the supercapacitors in the middle port. And the bottom solution has a high frequency transformer, hence we have isolation. So this is the summary of the analyzed high gain DC-DC converters. Also, I just put it as reference at a conventional boost converter. And we have to notice that if we want to increase the gain ratio, we have to put more boost converter stages in cascade. Hence, the efficiency will be at the power of n. So I just want to highlight that these are the two best solutions in high gain for supercapacitors because they have the wide input range operation and they have the highest efficiency. Moving forward, we have the multi-level converter, which is another solution for high gain DC-DC converters. We can put as many levels as we want. We can replicate like the basic structure of the multi-level converter to accommodate as many levels as we need to reach the desired voltage levels. Particularly, they are used in motor controller, but also they are used in multi-level inverter topologies. This is like the generalized version of the multi-level inverter topology. If we want to increase the number of stages or levels, we have to replicate this P2 cell. And if we start increasing the number of levels, then we have another benefit, which is the decreasing the total harmonic distortion. But if we continue increasing the number of levels or stages, we will create a very complex system with many transistors that need to be switched. And this is not a suitable solution for more than 9 levels. So another solution, it is to use modular multi-level converters. And this type of converters solves the scalability issues. And we can recreate a sinusoidal waveform at the output by simply switching switching on and off these half-bridge submodules. But particularly, they are used in high voltage direct current transmission lines. We have from the right image a half-bridge submodule for 6.5 kilovolts and 2 kiloamperes. So it is a system that is suitable for up to 2,000 megawatts. And for distances around 300 kilometers for transferring power. But recently, authors started to use the modular multi-level converter approach and to incorporate supercapacitors or other type of energy storage device in the converter. And particularly, I'm analyzing these 4 options. The first one uses DC-DC converters placed in series, and they incorporate the supercapacitors. This is connected at the DC bus level. The problem, however, with this is that we have an additional controller needed for these DC-DC converters. But the authors propose a solution for the low voltage grid applications. Also, if these DC-DC converters are optimized for supercapacitors, then we can have the wide input voltage range needed. Another option is to modify the modular multi-level converter basic submodule. In this case, it's a half bridge using an inductor to connect the supercapacitor. However, the problem is that there is just a specific point that the supercapacitor will be operating. And because supercapacitors are low voltage devices, we will have to put as many submodules as needed to reach the grid voltage levels. So eventually, the natural solution for this is to use a boost converter instead of just interconnecting the supercapacitor. And with this boost converter, we can reduce the number of submodules needed. We can have the wide input voltage range operation, and it is suitable for the low voltage applications. Another solution is to change the submodule and to use another type of submodule, which is a soft switching cell. And with this soft switching cell, we can have higher efficiency values, but this will only work on a certain range. And the controller must also supervise the soft switching ranges. And this was only validated with simulations. And the author proposed like another form to balancing the supercapacitors. So based on this literature review, I identified that in the traditional energy storage systems, there is the lack of flexibility. There is this issue with the fault tolerance. There are many stages needed to operate the energy storage system. there is, for supercapacitors, we have to have this wide input voltage range operation and the balancing, which is a must. And there are not so many solutions for modular multilevel converters, particularly for low voltage applications. So I'm proposing a modular multilevel converter that is suitable for the low voltage applications, and also that is suitable to incorporate the supercapacitors. So this is the proposed converter to the right. I'm not just only proposing to modify the submodule as authors proposed, but also to modify the series arrangement of the submodules. It is not like placing DC-DC converters in series, but rather with an special placement in the middle, from the middle part of the modular multilevel converter, which I will explain furthermore. So as regular in a modular multilevel converter, we will have two arms or two branches. We will have the top arm, which has his own reference signal, and the bottom arm that has another reference signal to generate the sinusoidal waveform. So if we want to generate the positive semicycle, we have to short circuit the bottom arm, and the top arm will provide the power for the positive semicycle. And the same happens for the negative semicycle. Now the top arm is short circuited, and the bottom arm is providing this negative semicycle. So as I already did the literature review with the high gain DC-DC converters, I proposed to use this full bridge with the active clamp. It's easy to control, it has good efficiency, and the wide input voltage range operation needed for the supercapacitors. And also with the transformer, we can have the galvanic isolation needed. So we have a modular system. We can increase the voltage levels if we add more submodules in series. And if we want to increase the power capacity of this modular multilevel converter, we can put the submodules in parallel. And also we have the wide input voltage range operation due to the submodule selected. So based on this DC-DC converter, we have to analyze it to see if it is suitable to be interconnected to an AC grid. So for that, we have to provide a bandwidth of at least 500 Hertz to have the DC signal, and then the AC 50 Hertz signal or 60 Hertz. So I did a small signal analysis for the submodules. And then based on that, I selected a type 3 controller for controlling the submodules. And I just want to mention that with this, the main controller will see the submodule as a simple transfer function, and the dynamics will not be coupled. So these are the both plots for the submodule. We have enough phase margin and gain margin. And remember that we have the submodules placed in series. So at the transfer function, it will be at the n multiplied by n. And the master controller can be implemented with a simple PI, which has to work in the DQ controller. And moving forward to explain how the self-balancing operation works, here we have like the top branch in detail, in which the submodule number 2 is not only supervising his own voltage, but it is also supervising the supercapacitor voltage of the adjacent submodules. So it is supervising these voltages, and based on these voltages and with this error signal, the proportional controller can slightly adjust the output power of the submodule or the voltage output of the submodule. And then the internal voltage reference for this submodule will be updated. And with this, we can achieve the self-balancing algorithm. Hence, the master controller will not need to supervise all the submodules, all the voltages of the supercapacitors, and it only needs to set the reference signal for recreating the sinusoidal waveform. So this is how I achieve the balancing system, and I will show in a minute how this works in reality. So we have a system that reduces the many stages needed in the traditional energy storage system. We have a system that can achieve the balancing system, the DC-DC conversions, the DC-AC inverter, and because we have the high frequency transformer in the submodules, the galvanic isolation as well. So the system is, we reduce the many stages needed to just a single stage, a single series arrangement. And the solution can be suitable for low voltage grid applications and with galvanic isolation as well. So moving forward, I just want to mention that I did 2 prototypes to validate the converter. The first prototype validates the operation and with the AC waveforms. And the second prototype is an optimized version with 4 supercapacitors per submodule, which I will describe in detail. The first one is already published in an open access journal. And in the results, we show the load step change with a resistive load, and then from a resistive to an inductive load, and from a resistive to a capacitive load. This validates the 4-quadrant operation, and also all the submodule analysis and everything is published under this journal article. Also, I tested the efficiency of the submodules. As you can see, the efficiency is stable along all the power range, and it is also stable in these 2 corner voltages, 2.7 volts, which is the most charged value that we can reach, and 1.7, which is more or less considered to be discharged at 75%. As you can see, the efficiency was not so impressive. So that's why I started to work on the efficiency to analyze how these, where the losses were coming from. And I did a model that takes into account the transistor switching losses, the conduction losses, and the core losses. So the model considers a discharging cycle. It calculates the losses for balancing the supercapacitor stack. Then it calculates the MMC level balancing losses. And this is done for all the submodules presented in the modular multilevel converter. And after that, we extract the load power from this specific time step. And then we recalculate the voltages of the supercapacitors. And we save this efficiency value. And this is done till we end discharging the supercapacitors to accommodate like a whole cycling of this energy storage system. This is done not only for 1 supercapacitor per submodule, but also for 4, 7, and 9 supercapacitors. And I'm testing this in Python for 10,000 cycles with varying the initial conditions for the voltages of the supercapacitors and the capacitance of the supercapacitors. This is like simulating the degradation that the supercapacitors will have during the time, and also to understand how the balancing process will take part if the supercapacitors are not balanced. With these 10,000 cycles, we can create a cumulative distribution function at 90% of confidence value, and we can get the efficiency value for this particular energy storage system with 1 supercapacitor per submodule, 2 supercapacitors, 3 and 4, and so on, till reaching 11 supercapacitors per submodule. So based on this, I saw that for unbalanced conditions with 4 supercapacitors per submodule is the most optimal value, particularly for the low voltage grid applications. And with that, I did the last prototype to validate the results. With this plot, I'm balancing internally the supercapacitors at 11 seconds. And then when the load is connected, the modular multi-level converter self-balance technique starts to work and balance the submodules at the end. So at the end, we reach 100 millivolts of difference from the most charged supercapacitor and the most discharged one. So the efficiency of the submodule is now more high as we were expecting with the simulations, with the theoretical curve. And based on these experimental results, I then interpolated this curve and feedback the model. So with the model, I can analyze for a complete energy storage system a 16 kilowatt for low voltage applications around 220 AC volts. And in comparison, we were expecting like 95% of efficiency. We obtained for the real prototype 93% of efficiency with a 95% of confidence. So moving forward to the conclusions, I have a system that can achieve all the needed stages in the traditional energy storage system: the balancing of the energy storage devices, the DC-DC conversions, the DC-AC inverter, and the galvanic isolation as well. The validations were done with 2 working prototypes and with simulations. The first prototype validated the operation of the energy storage system. The second prototype shows the feasibility to be implemented in low voltage applications without the efficiency drawbacks. And finally, the model that I presented can be useful to analyze and to scale the proposed energy storage system to a higher voltage or range or power range, or to use a different type of energy storage device. In the future work, I want to focus on correctly sizing the power capacity or the type of energy storage device. Also, I want to perform internally the balancing system in a single stage, maybe to incorporate this in the DC-DC converter, or see another type of applications. It can be for vehicular applications, for UPS systems, or for a tram or for a train. Therefore, if we want to have like a large bulk electricity storage, it is suitable to analyze the integration of 2 or more storage devices. And also, I was just testing the energy storage system with a grid following algorithm. I want to test with a grid forming control just to see that the prototype works. So I attended 2 renowned conferences as first author, and this is the list of publications. And I have a 3rd journal on the review in the International Journal of Electrical Power and Energy System. Particularly, I'm presenting here the optimization done for improving the efficiency of the modular multi-level converter. So thank you so much. It's all for my presentation.
Thank you very much, Fernando, for this presentation, which was done within the time. We now can start the questions from the jury. And we will start with our external jury member, Pallavi. We cannot hear you now. I mean, your mic is...
Yeah. Thank you so much. It was a nice presentation. I have a few queries, Fernando. Is the system proposed by you a bidirectional system?
Yes, it is bidirectional. It has to inject and absorb energy from the grid.
Okay. So have you done any bidirectional analysis on this? Like, have you done the charging part also? Analysis of the charging part also?
Yes, I tested the efficiency for both charging and discharging the submodules, but only the interconnection to a grid was only with simulations.
Okay. Have you integrated the system on a single phase grid or a 3-phase grid system?
We did just for the single grid, and we propose a solution for a 3-grid phase system.
Okay. Now, can you please go to slide number 11 of your presentation.
Yes.
Yes. So in this slide, my question to you is, have you compared this system, like the system DC to DC, AC to DC, and isolation, the whole system with any other energy storage device apart from supercapacitors? Is this system, can we validate the system for some other energy storage device, like let's say battery of electric vehicle?
I was doing the analysis only for the supercapacitors, but we can replace the energy storage device. We can use a Li-ion battery and then do like a comparative with the traditional topologies and the proposed topology.
Okay. Can you please move on to slide number 23? Yeah, go back to slide number 15 actually first.
Which one?
15, 15. Yeah. 15.
Yes, sorry.
Right. So the DC to DC converter which you have utilized for your proposed system, is it a DAPS? Is it a dual active bridge topology, or is it different? Because in that DC to DC converter topology, I can see that it is a DAP topology. Go to the DC to DC topology.
Yes, it is a full bridge topology. It has an active clamp, so we can reach in some intervals 0 voltage switching.
How did you achieve soft switching in your DAP topology?
The clamp is activated. I will put I think this is better seen in the submodules here.
Yeah. How did you achieve soft switching here?
When we activate this clamp, the energy that is released from this capacitor will slightly increase the duty cycle of the converter. And for the next, now that this transformer is discharged, the next switching will occur at 0 voltage switching.
And how bidirectional flow of power was possible in this topology?
Yes, bidirectional power flow is possible because all the switches are transistors, are MOSFETs, and we can achieve the bidirectional power flow.
No, what is the condition of bidirectional power flow? Is there any, phase shift control which you applied here for the bidirectional power flow?
Okay, if we are transferring energy from the voltage feed section to the current feed, it is phase shifted with these transistors, and these other transistors are working in active rectification. And if we are transferring energy from the current feed section to the voltage section, this is with the boost, like more related to a boost converter. We put in short circuit for a short time the inductor, and then we release this energy through the transformer.
No, my question was, what was the phase shift angle between these two bridges? It's a DAP topology, and in DAP you can transfer power from one bridge to other bridge by changing the phase shift angle. So what was the phase shift angle in your topology?
So okay, the duty cycle or the phase angle is controlled by the controller. If we want to recreate a sinusoidal waveform, this phase shift is varying to discharge the supercapacitor and to have to accommodate a voltage at the output of the submodule to recreate the sinusoidal waveform.
I'm just going to ask you a very basic question. You have used, are these switches IGBT or MOSFETs?
I used only MOSFETs for
MOSFETs.
because
Why
I
these
was just-
diodes? Why these diodes are connected across those MOSFETs?
because this is the internal diode that the MOSFET presents. Just
What
quite
is the importance of these diodes?
is the freewheeling diode just in case.
Fine. Can you go to slide number 13, please? 30. 39.
39.
Yeah. Okay. I just missed that part. You were saying that efficiency is not so good.
Yes, in the first prototype, I was using just a single supercapacitor per submodule. Hence, the submodule was operating on a very low voltage from 2.7 volts, which is the most charged value, and to 1.7 volts. The efficiency was not so high because of the current that was involved in the converter. But the main aspect is that the converter works in these two voltage regions, and that the power is stable in this long range.
So is this the efficiency of the module or the complete converter? I mean, the complete system?
It's the efficiency of the submodule, but we can interpret that this is going to be the efficiency of the complete modular multi-level converter. Only the submodules will slightly adjust the power output, and it will be moving to balance the supercapacitors, and it will be moving very closely to these efficiency points, and hence it is going to be like the overall efficiency of the system.
Okay. Now, moving on to multi-level inverter, can you please go to the slide showing multi-level inverter topology?
This one or?
No, the MLI topology where the circuit diagram of multi-level inverter. Yeah, this one. So, have you analyzed the effect of this multi-level inverter on the power factor side and the harmonic side? Like, what was the THD of this at the output of this MLI?
Because I was using each submodule was switching with a 100 kilohertz switching frequency. The THD was very slow, very low. I didn't put like the specific value, but this can be analyzed in the future.
And what about the power factor? Like, what was the power factor while incorporating this MLI? Because, in your first introductory slides, you have mentioned that the THD is improved and power factor is improved. So can you say something about the power factor by incorporating this MLI? Do you think the power factor was improved using MLI?
Rather than improve, we can control the power factor because I'm proposing to use a DQ controller in the DQ frame. Let me just reach this part. Just for the simulations, I was just controlling the D of the proposed energy storage system, but no, I didn't analyze further the power factor impact.
Because when you're working on grid, when you're interfacing something with grid, you must mention these two important parameters. Like if you are adding some converter to the grid, the analysis of power factor and harmonics is a must. I mean, some numerical value must be there. Anyways, you have analyzed the efficiency part of the system. One thing you have mentioned that modularity or scalability is not possible. Is it possible here in the system?
Is it possible to what?
Modularity or scalability is possible of your system?
Yes, because if we want to increase the voltage, we can add more submodules, or if we want to make a redundant system, we can add more submodules in series. Or if we want to increase the power capacity or the energy storage capacity, we can place them in parallel.
Fine. And what was the level of the stepped output of your MLI?
For the voltage that I reached, or
level? Yes. How many level of MLI you have used?
So the submodules can reach 10 volts at the output port. So if we want to accommodate for a single phase system, we will have to place 40 submodules in series, but the submodule can be redesigned to have a higher voltage to reach higher voltage levels.
Fine. My last question, can you go to the introductory slide where the block diagram of the system is there?
Of
Of the system, the
Of
whole
the-
system. No. Of AC to DC converter, DC to DC converter, and the storage system. Oh yeah, this one. Can you mention the the voltage and current ratings at different levels? Like at the can you mention the DC link voltage and current? Can you mention the voltage at the transformer end? Can you mention the voltage at the output of the storage capacitor here?
Okay. Normally for supercapacitors, because they are low voltage devices, we will have a voltage level here at this port at 48 volts. If we want to work in a single phase system. And then after the DC-DC converter, we will have a 400 volts in the DC link, which is going to be suitable for the inverter to be then interconnected to the grid.
And what about the output of DC to AC?
The
at the
output
primary
current,
side of the transformer?
it will depend on the power that we want to reach. If we want to reach like
No, for your prototype.
For my prototype, I was reaching a 16 kilowatt system, but this was only just tested with simulations.
Okay. So can we interface PV in this system? Like you have storage cells here and you have grid here, you have all converters here. Can we interface a PV system with this system?
I think it would not be possible to incorporate the PVs because the PVs will not provide like the energy buffer needed for the DC-DC converter to operate. In this case, maybe we can select another submodule or another topology for the submodules to have like 2 ports, one for the PV and one for the energy buffer.
No, but a 400 volt DC link is there. And if suppose if I want to interface one PV system, what I need is a DC to DC converter, boost converter along with a PV. I think we can interface. Anyways, that's all from my side. Thank you very much.
Thank you very much, Pallavi, for your questions and this very interesting discussion. I would still like to ask you if you are satisfied with the changes that Fernando did following your review of his thesis.
Yeah, I have, I've gone through those changes, and I'm happy that all those changes which I have asked him, we have incorporated all those changes.
Right. Thank you very much. Thank you.
So much.
So now we may turn to our other external jury member, so Dr. Vedran Peric. So if you have questions for our candidate, please proceed.
Yeah, thank you. First of all, thank you for also a nice presentation. So I almost regret reading the thesis since you presented it so clearly. So yeah, thank you for that. You made it very clear, actually, what are your assumptions and what are your objectives of your thesis, which I really like. So you want to do this MMC topology with supercapacitor to increase efficiency, and there are some problems with the wide range of control. So this is at least what I got like as bullet points, what is really important. Also, what I liked is actually experimental setup. So this is, I think everyone who actually did some work in the lab, there are always many hiccups there. So this is also something that I really like about the thesis. So enough of praising. So now we'll go to a bit harder part. And actually, I will start with a quote from Elon Musk. Usually he says that the most common mistake of the engineers is that actually they are optimizing something that should not even exist and not just be optimized. So I'm not saying, of course, your work is like that, but I would like actually to go more on that line and ask, where do you see really the application of this? So these are assumptions, which is very theoretical, what needs to be done, and it's very scientific approach. But let's assume we solve this problem. Where do you actually see this going step forward?
So the step forward is to incorporate this in a system that requires the extended lifetime of the supercapacitors and the many cycles that they can reach, and in a system that maybe later has to be the voltage has changed and the demands of the current and everything has changed. So I was thinking in the grid, but maybe there are some other applications that this converter is more suitable for it.
That's exactly my question. You mentioned your motivation was the grid, but then, of course, you were talking about wind power, renewables, but then we are talking about much larger actually voltage levels, and then it's a bit difficult actually to scale, at least in my head, your experimental setup with this application. So now you mentioned, okay, some other applications. So where do you actually see the main application of this?
Maybe in an electric vehicle that has to do these many cycles, and maybe in a company that has to increase the capacity and then or the size of this electric vehicle in a tram or something like that. Like they can add another stage and increase the power.
Okay, that would be also my advice, actually, to have this more engineering than approach, to have really clear application in mind and then actually develop the solution for that. Even, of course, sometimes it goes hand by hand. I know that also starting from some assumptions, develop something and then see the application. But okay, so you decided to use MMC, and yeah, this definitely brings all this balancing, and there are some good sides, but you didn't really mention what are the bad sides of using MMC topology.
The MMC topology at the beginning will be like, it is an expensive system that has many submodules, but at the end, this system is flexible, it is upgradable, so the cost benefit will come in the future, not at the beginning. In the beginning, it will be costly to implement, maybe. It will depend on the cost of the final submodule.
Okay, so you mentioned then electric cars, so I suppose you would then also apply this with lithium-ion batteries?
Yes, this can be, because the balancing can be achieved, Li-ion batteries need this balancing too, so this can also be used with Li-ion batteries.
So what would be the difference, main difference comparing to the supercapacitor and lithium ions?
In the lithium-ion batteries, there is not this need for the wide voltage range. Maybe we can select another DC-DC converter that is suitable for this. Maybe it is not even needed to have this galvanic isolation, so we can change the topology of the submodule.
Then going to that direction with the cars, so there is actually a big issue with the cars, actually what to use with what to do with the batteries once they are used. So do you think actually this topology can help in that direction? So what do we do with these second-hand batteries?
We can recycle them. Maybe we can use this because in my head, I was thinking this for bulk energy storage or for a static position of the converter, but this can be done with not only supercapacitors, but with the batteries, and in this case, the recycled batteries.
But are you aware what is actually the main challenge there with these second-hand batteries and building a stationary systems with these batteries?
No, I haven't go deeply on detail on this, on what happens with this type of batteries. Actually,
it's why I'm asking that, because your topology is actually quite suitable for that, because the main challenge there is exactly the balancing, because the problem with the batteries is that they are aging in a different speed, and then actually balancing the aging is actually quite good. So if you would manage actually to put this kind of a converter actually in the car, I see at least a quite interesting potential. So, okay, next question. So you did actually small signal analysis. What would be actually the limitations of that analysis? In a sense, what you cannot say from this analysis?
So I think that the main drawback will be if we put too many submodules. Maybe we will decrease like the controllability of it, but we haven't like just studied in detail what will happen with many submodules.
But do you have some non-linearities that are actually neglected in this study?
No, we were just assuming that the transfer function will be like a simple one, like this. At the end, it will be just simply to see like this second order transfer function. But we haven't like actually tested like with these many submodules placed in series. What will happen.
But how accurate that assumption is?
Yes,
You just said, okay, we assumed it behaves like this.
Yes.
But how accurate it is?
No, we haven't tested. Maybe it will be good to variate a little bit the values of each of the submodules in the transfer function to see what will happen at the end.
Okay. One question actually that kind of puzzled me. You also mentioned that once you design this like a traditional system or like kind of drawbacks, the power is fixed. You use this term, right? If you remember. So why it is fixed actually? In which way its power of the system is fixed?
I'm just like the stages will be fixed around this power constraint because they want to increase the efficiency of the overall system, but they have to accommodate or to design these individual stages around this power. So like the whole system will behave with the efficiency they want for that.
But you can still stack them in parallel, right? Or not?
Yes, you can place these traditional energy storage systems in parallel. You can start increasing, but you will not have like so much degree of freedom to, if you want to go for a 15 kilowatt system and you already have a 10 kilowatt, should you put another 10 kilowatt system or what? You will have like these some gaps that cannot be filled with the traditional energy storage system.
Mm-hmm. Okay, so you mentioned also you have these 4 applications and the 5th one is under review. So how would you actually rank them? Which one is, if I need to read only one of your publications, which one would be that be?
The important one will be the one that validates the proposed modular multilevel converter. The other are just contributions to the topic, to the modular in the modular multilevel converter energy storage systems. And another one is focused on the dual port DC-DC converter. So I want to explore in the future to use this dual port converter in the modular multilevel converter. But this one is the most important one. And the one that it is under review presents these analysis losses, this efficiency losses analysis. And this was done with Python. So I coded this and the results are like quite good. It is another approach to optimize this type of energy storage systems based on the modular multilevel converter.
Okay, and maybe the last question from my side would be, what are the unexpected results actually that you faced during this PhD journey? So what was something that kind of changed your view from the beginning?
So the unexpected results were like when testing each of the submodules, I was like putting one, and then I made a mistake. I made a short circuit, and then this submodule was burned. So I had to start like working again because I cannot test the three of them if one of them is failing. What will happen when this fails, it will put in short circuit, so the others can continue working, but this one is not providing voltage at the output. So I was like seeing this in the oscilloscope, like why I'm not reaching the voltage that I need. So because one was failing. And also it was quite complex to calibrate the voltage sensing in each of these microcontrollers for the supercapacitors. And the other aspect was that the authors, that the reviewers, when we were trying to publish the articles, like they were not seeing how the submodules were arranged. So they were like, it's just a normal series arrangement of DC-DC converters. So it is not new. But the novelty resides in how we can achieve the sinusoidal waveform without creating like a very complex system to manage.
Okay, thank you. I don't have further questions.
Thank you very much. I have to then ask you, Vedran, the same question. Are you satisfied with the changes in the thesis, the revisions after your review?
Yes, I am satisfied. So I recommended actually making this appendix at the end, and this was actually included in the final version.
Very
Thank you for that.
Thank you very much. So now we may ask our colleague, Dr. Piotr Vorobiov, do you have questions for our candidate, please?
Yep. Yeah, I'll turn off the video just. Yeah, I have a couple of questions. So one of the questions is, yeah, well, first, thank you for this very good presentation. Yeah, it's really impressive. So I have a couple of questions. One question is like technical, and another one is like more general. So I'll start with the general one. If I understand it correctly, for supercapacitors, probably the efficiency of conversion is not something that is super important. So am I right? And if I'm right, what are those parameters for the converter that are especially important for applications with the supercapacitors?
With supercapacitors, we have to we need to have like this high power transfer ratio or this high power. So the DC-DC converter has to reach these power levels, and also to operate on this wide voltage range, which is like a must for the supercapacitors.
Okay, and how about the bandwidth of your converter? Is it like important to have like really these capabilities to regulate fast?
Yes, if we want to interconnect to the grid, we need to satisfy like the submodules can have like at least the 500 hertz that I was aiming for, but it could be faster if we want to explore like different applications for the grid or for another.
But that's just the grid requirement. It's not like something specific to supercapacitors. Or is it specific to supercapacitors?
No, it is not. I think it is not specific for supercapacitors. Okay.
Yeah. So then I have a technical question. I think on the previous slide we have this series. Yeah. So if you interconnect in series those modules, what that means is that you're gonna have like an overall transfer function of a pretty high order. Yeah? In general, that actually raises the questions of stability. because you can have your PI tuned for one module, and that's perfectly fine. And then when you start inserting more modules in series, you can have like really, you can start having stability problems. Did you see something like that? Or maybe just had to adjust the controller to deal with that?
So at the end, the master controller will see the transfer function of a single submodule multiplied at the end, at the number of the submodules. But in the simulations, everything was like working fine.
So multiplied or in the power of that? Because if it's a series interconnection, then it's not multiplied, it's the power. If it's in parallel, then it's multiplied.
But each of the submodules is contributing with their power transfer. So it is multiplied in this, like in this arrangement, in this specific arrangement. Each one is behaving like a parallel converter contributing to the overall power output of the system.
Okay, in this case, yes, because when you write it like a series in this control block diagram, if it's series, then it's not the multiplication, it's the power. So you have to be careful here when you describe that, because series interconnections in general are some kind of like red flags in control, in a sense that if you have any rules specified for certain control blocks and then you connect in series, that's the first thing that you see, that you have to do additional checks. It's not something that probably is important for your particular realization, but just in general, that's a suggestion. Yeah. Okay. Yep. That's all on my side. Thanks.
Thank you very much, Piotr. Now I have to ask you if you are satisfied with the changes and the revisions of the thesis following your review.
Yes.
Okay. Thank you very much, Piotr. So now our colleague, Professor Jelena Grezina, may ask questions and make comments.
Thank you. So first of all, thank you for the presentation. It was indeed very clear with making the very clear, very well explaining all the peculiarities. Thank you for this. So my first question is like, is it correct that we can treat every submodule as an independent energy storage system?
Yes, since each submodule will have its own supercapacitor, and the power it is flowing from the submodule through the overall series connection.
So it means that like your customer may decide him or herself how many submodules are needed, and you can just come up with arbitrary number of submodules in the system, or it's not exactly like this.
For a final application, or?
Yeah, for a final application. For instance, well, I have an application, then you tell me, okay, you need this number of submodules, and that's fine. Or for the other application, I have like twice more submodules, and you connect them, and it works. Or it's not so trivial, like depending on the number of submodules, the general behavior of the system changes, and you need to tune something in the system. Or they are like plug and play, you can connect arbitrary number.
So yes, at the end, we want to reach like a plug and play system. We have to test like what will happen if we keep increasing the number of submodules. And but related to your question, if we want to increase the power, we can place these modules in parallel. Maybe for your specific application, you will have the single phase system, but with a lot of power. So we will have to place the submodules in parallel. You will have a large number of submodules, but they will depend on the arrangement, on the final power budget and the voltage budget, the number of submodules.
So can you can you propose any really large number of submodules such that it doesn't make sense to increase it more, or you need, or some extra research, you need to tune your system the other way or something like this, or if you can infinitely increase the number of submodules?
I guess we cannot infinitely increase it, but I was aiming this for low voltage applications around 220 to 400 volts. Maybe if we want to work in the middle voltage level grids, then the submodule has to be redesigned, just to don't end with so many submodules placed in series.
Okay, understand. So now let's talk about the number of supercaps per submodule. So in slide 41, I guess you have this experiment, well, comparing the different number of supercapacitors for each submodule, and you test the specific numbers 1, 4, 7, 9. Does it mean that it doesn't make sense, like engineering, going beyond 10, or there are other reasons around it?
Just for this plot, I just plotted these ones, but here I tested for up to 11 cases. I thought that if we keep increasing the number of supercapacitors, there is no so much benefits in the efficiency. So that's why I just stopped there. For each supercapacitor increase, we have to calculate or select the transistors that should be suitable for this arrangement. And based on this, we can see that if we keep increasing the number of supercapacitors, the histogram will be like more broad. So the efficiency will be varying a lot. So that's why if we keep increasing, then the efficiency at this 90% confidence value will not be as in the previous cases.
Okay. Okay. So you can actually come up with the optimal number of supercapacitors around 5, something like.
Yes, more or less around 4 or 7. 7 was the highest for a balanced condition. But we also take into consideration like the complexity of having these 7 supercapacitors, and then having to do the internal balancing of these supercapacitors, and then the modular multi-level converter balancing, and so on. So this was like taken into consideration for selecting 4 as the optimal value.
Yeah, and that's also the reason why you should not go for larger numbers, because you need to make internal balancing among them. Okay, fine. My other question is about, can you go to the slide describing this balancing system? Actually, when you were talking about here, I had in mind the analogy of consensus, which takes place in decentralized or multi-agent problem. So is it like something, do they do something similar like consensus? Do they need to equalize some numbers between the submodules?
I'm not familiar with the consensus term, but,
yeah, but what's the goal of the balance? So what do we need to equalize some I don't know, quantities, some voltages?
Yes, the voltage should be equal for all the supercapacitors. Since this is going from one submodule to another submodule, it will take time to reach the whole balancing operation. But this was tested in simulations and in the practical part, and they can reach a balance in just one discharging cycle.
I see. Well, but that's exactly consensus. It's like you have a number of agents and they need to reach consensus. Their variables should finally take the same values. And the question is how to properly organize information exchange between them, how they need update the number of their variables in order to reach this consensus. And there are like different protocols to do it. So I think it's what you are doing here. It's something similar to this consensus issues.
Yes, so each submodule is like supervising the other submodules adjacent to them, but the following submodule will not see the voltage of the supercapacitor of submodule 1. So it has to slowly reach the global balancing voltage.
Yeah, but it depends how you organize this exchange of information.
Yes.
So maybe you can update it a little bit to make it faster if necessary. Okay. And well, the other question I have is about losses reduction. So like when you checked efficiency, you were not satisfied with certain structure, and then you made some changes in order to increase efficiency. So how much efficiency was increased, and like how much you expected it to increase, and how much you actually observed what time of increase in
Okay,
efficiency?
yes. So when doing the first prototype, I was aiming for 93% of efficiency in 92. At the end, the submodule was not so efficient, mainly because of the high currents that were involved in the supercapacitors and the low voltage that was provided by the supercapacitors. So at the end, I was not satisfied with this. I started with the efficiency losses analysis, and this is like shown in the thesis. It is a table that shows the component list for each of these cases, 1, 4, 7, 9, also for these other cases. So we can see that, yes, this is what I was aiming for for a single supercapacitor, almost 93% of efficiency. But at the end, in the prototype test, it was not as high as we wanted. So that's why I proposed this methodology to assess the losses and also to assess that the balancing can be achieved with different number of supercapacitors. And this is like the final prototype. We were expecting 95%. We reached with the system with 93%, more or less.
Okay, but your original expectation, like 92, 93, was it kind of because it's a benchmark that was reported in the previous work that it could be, or it's kind of theoretical estimate?
Okay, in the traditional systems, more or less, they are aiming for this 94%, 92%, taking into consideration that in the traditional system, the stages are in cascade, and each of the stages will contribute to the overall efficiency of the system. So the DC-DC converter will have an efficiency value. The DC-AC inverter will decrease, will add more losses to the system. And hence, at the end, we will have a system that has less efficiency than a single stage of the overall system.
Okay. Okay, I think that's all from my side. Thank you for addressing the questions.
Thank you very much. So Elena, are you satisfied with the changes in the thesis?
Yeah, I'm absolutely satisfied with how the comments were addressed.
Thank you very much. So now it's my turn, and in fact, my questions are just like clarifications to see, I mean, basically your vision, because you speak about flexibility, but it's not like you define clearly what flexibility means, what would be something which is not flexible, and flexible if that can be, for instance, quantified. You see in slide 24, you say, okay, lack of flexibility. How do you decide when it is lacking flexibility?
So as I was mentioning, you already have deployed a system for 10 kilowatt or 20 kilowatt. If you want to increase just slightly the power, should you put another 20 kilowatt system, or we can just add just a single submodule, another extra submodule or something to increase this this power rating.
Yes, but then what you're saying, it's like empirical.
Hmm?
It's empirical.
It was just like thinking how in the industry they release energy storage systems for the industry, and how can we improve this with another type of topology, with another system arrangement.
Yeah, but I'm insisting a bit on this because when we speak about grid flexibility, for instance, so this is about it's flexible when you can have any topology, or what? I mean, can you go further into this definition of flexibility? I'm insisting a bit.
No, just flexibility in terms of implementing the resulting system.
Because, for instance, flexibility, I mean, if you're not flexible, is it related also to stability, for instance? Are you, I mean, less flexible when you risk more instability or not? I mean...
Okay, no, I see your point of view. It is just flexibility in terms of power, but not in terms of the system should operate as the grid codes demand.
Mm-hmm. Yes, because I mean, it is always important to make sure that when you use something like flexibility or other thing, that we understand exactly what this refers to. Pallavi, at some point, she asked a question about integration of, say, your solution. I mean, you said it is in a one-phase grid, yes?
Yes.
And that you are thinking about three-phase, yes?
Yes.
What would be the challenges? I mean, what would make it easy or not easy to go from one phase to three phase?
Okay, so just go. So depending if we want to have like a balanced three-phase system, yes, the arrangement should be special to share a neutral connection.
Yes.
If we want to have just an unbalanced three-phase system, we can replicate the same modular multilevel converter and place it for each of the phases. But yeah, this has to be like tested further for a balanced and unbalanced three-phase system. I just briefly described this on the thesis, but it has to be like future work also to be analyzed.
But do you expect this future work to be easy to implement? Like, would it be the work of 1 month or 6 months or more? Difficult to guess.
Difficult to guess. Yes, maybe it has to be.
Yes, but make an educated guess now that you're going to be a doctor.
The educated guess, it's that first, I think it is going to be pretty straightforward to implement this on an unbalanced system. It's just replicating the same arrangement. But what we have to test on detail is sharing the neutral connection, just to that the controller must satisfy that there is no current flowing through the neutral. So,
but the total number of submodules would not be an issue.
The total number of submodules will not be an issue. Maybe yes, because in the proposition that I have made, we are duplicating the number of submodules, so this can be an issue. I'm aiming to use 40 submodules per single phase system. In this neutral connection, it will be 80, so maybe it will be too many submodules and has to be tested experimentally.
Yes, right. In slide 40, following a question by our colleague Piotr Vorobyov, you spoke about transistor switching losses. Yes?
This one, yes.
Yes. Can you explain, let's say, a bit of the physics of these losses? What do we lose and why?
So when switching transistors, there is an energy that is lost in the transition of on and off. And
but under which form? Like electrical energy, under the form of heat? How?
In the form of heat. It will be dissipated through the transistors. And this energy comes, of course, from the supercapacitors or from the grid. And also there are some conduction losses because the MOSFETs cannot be like a perfect wire.
Mm-hmm.
And this will create more heat to the system. And also the core losses of the transformer and the inductors.
But with increasing heat loss, I mean, locally you have increased temperature of your system, yes?
Of the submodule,
Yes.
only of the converter.
So how does that affect? I mean, is there some sort of, let's say, I mean, the warmer or the hotter they are, the worse it is for the losses or not? Or is there some balance at some point and you get like constant loss?
Yes, so the power limit is fixed based on this constraint.
Mm-hmm.
Each submodule has a heatsink, but like this is given by the transistors that I was choosing, by the MOSFETs chosen. But maybe in the future, with better transistors, we can accommodate more power in the submodules.
But how would you manage I mean, did you think about the management of the excess heat?
So
because in your system, you don't address this this particular point, I believe.
No, for each submodule, we have a heatsink attached in the transistors. The transistors are in the backside. Of course, we do not want that this heat goes to the supercapacitors, because if these supercapacitors get warmer, we will decrease the lifetime of it. We will dry the supercapacitors. That's why I just put it like in a separate connector.
Yes.
Just to isolate from this heat source of the DC-DC converter.
Okay, thank you. On slide 41, you see we have a drop of efficiency for 5 supercaps per submodule, yes?
Yes.
So how do you explain this trend here in efficiency for this number when it is 5, then you have a drop like this? Is there a reason for this?
Yes, in this module we have a transformer, and I am also modifying the turns ratio of the transformer. So if we keep increasing the supercapacitors, we have to reduce the number of coils for the transformer. But in case 5, there is like the particularly that we need to have more the same number of coils as in case 4. But with the additional voltage that has to be like put. So it is having more losses because of this extra coil.
Okay. So thank you for clarifying these few points, which show to me that you have, let's say, a rather clear vision of what you're doing, which is important. So I'm satisfied also with the changes that you did in your thesis after the reviews. So, okay, now we may turn to the audience, offline and online. So if there is someone who would like to ask, of course, a technical question, I mean, a question related to the PhD thesis, they are welcome. So, I mean, do not feel forced, of course, but so no questions, no question offline. Online, I do not see anyone who would ask a question. Okay. So then I'm turning to the supervisor, and it is time for the word of the supervisor. Please, Professor Ibanez.
Okay, thank you, Professor Dan. So, well, I would like to have a few words about Fernando. Fernando started here as a researcher, a junior researcher, finishing his master thesis when we came. We create this idea of this energy storage system. Actually, one of the things that we were discussing, and I think Fernando didn't mention, is that the size of the converter is even smaller than the device. And if you see other devices in practice, usually the electronic system is bigger than the battery itself. So we were thinking something like a box when you have everything together, you just plug it. And I think we reach more or less this objective, although the efficiency is not the best, of course, and they have any other issues, as Fernando already mentioned. So in general, I'm very satisfied of Fernando's performance. Particularly, he goes through the pandemic situation, then well, other situations, and he managed to finish his research. He managed to publish some decent amount of publication and conferences. And as you see, Fernando is a very hands-on engineer. So he loves to test and retest and retest the devices. So I am very happy because I have the same profile. And yeah, so I think it might have some imperfections, but it's something that really works, not just in the computer. That's it for me. So I'm happy with the final results.
Right. Thank you very much for your word. Now it is time for the closed deliberation. So I will ask people here, not members of the jury, to leave the room. And online, there is a breakout room for the jury members. Right, so Fernando, on behalf of the jury, I would like to congratulate you. We unanimously decided that your thesis, I mean, the outcome is positive, and the thesis is accepted as is. So you pass, and you've done a very good work, which we appreciated, and even more so that during the last 4 years, things were not always that easy. I mean, and you managed to show some resilience, some commitment, and you reached your objectives. So we're very happy of this outcome, and your thesis, has reached some very, very good standards on par with, let's say, international standards. So we're very happy about this, and we congratulate you again on behalf of the jury. So congratulations.
I just want to thank my supervisor for all his valuable time, to the jury members for their comments on the thesis, and to my individual doctoral committee, and to my wife for being there always to support me. And of course, for my friends of Skoltech, I really enjoyed the time spent and all the discussions and ideas that we had together, and not only the Mexican team, but also in the lab team of the energy systems. So thank you so much.
Thank you very much. Congratulations.